After 36 months, 2,050 pairs of hands on deck, 800,000 bags of cement, 10,000 tons of reinforcement steel, and more than $500 million, the Kariba South Hydro Extension Power Station is now fully operational. With 300 megawatts added onto the national grid and increasing the station's capacity to 1,050 megawatts. For 4 years, the construction team has been working in the lion-infested African wilderness to get this high-voltage megastructure powered up.
From the waters of the Zambezi River rises one of the largest concrete structures in the region, the Kariba Dam. Situated in Gwembe Valley is the Kariba Hydroelectric Scheme, housing the Kariba North Power Station on the Zambian side and Kariba South Power Station in Zimbabwe. Construction of the dam wall and initial Kariba South Power Station took place between 1956 and 1960 with a total capacity of 666 megawatts from the 6 units. In 1997, the units were uprated to 125 megawatts each to give a total of 750 megawatts.
Generally, power generation projects require a lot of planning, and the planning entails carrying out pre-feasibility studies. In this particular instance, we had to study the rock where we were going to drill the powerhouse. The powerhouse in the southern part of the Zambezi River is based in a very, very unstable geology, and we had to make sure that we carry out detailed feasibility studies to ensure that we don't end up affecting adjacent assets and the demo.
In 2012, the State Procurement Board awarded the $354 million tender to Sinohydro of China for the extension of the existing power station with 2 additional 150 megawatt units. The total cost of the project, including development costs, was $533 million. Financing of the project was made possible through the China Exim Bank, Standard Bank, Infrastructure Development Bank of Zimbabwe, as well as the Zimbabwe Power Company's own resources. At the end of the civil construction period, there was a total saving of $4,942,219.90.
China Exim Bank put in 320 million. We did all the documents and then we presented them to government. So it was a government-to-government loan which Minister of Finance signed, and we were required to put in 10%, which is about 35 million. So we had to look for that on our own. With the help of government and other stakeholders, it became possible that we fund Kariba.
After the feasibility studies, we had to go out to look for a competent EPC contractor, the engineering, procurement and construction contractor. We carried out due diligence on him to ensure that whoever we had to appoint, in this case Sinohydro, we had the competence to deliver a project that as complicated as the one that we are carrying out. And also the fact that we were not doing major projects of this nature before. We wanted to make sure that the personnel that we're going to make use have the competence to deliver a project of this magnitude.
So at the moment we are working with Sinohydro Corporation, which is a subsidiary of Power China. They are a contractor who has done similar projects in more than 40 countries the world over. If you visit China and see some of their establishments there and some of the projects that they've worked for, you will realize that we are dealing with no amateur. We are dealing with a contractor who is aware of what's required of them.
For this project, China government to know this project is a very important project to mitigate the power shortage to this country. also very important to the people. Once we apply the loan to the China Exim Bank, China government give the very high priority to the project.
The fact that we are constructing a power station for the first time after about 30 or so years, the major problem becomes our technical readiness to construct such power stations, and also bringing confidence into people who are already in the system that this is doable.
Yeah, our economy is going to grow. As a result of the growth of the economy, we will need more power. There will be a consequential need to undertake many more of these projects, either through government or through private sector investment.
Energy is a key driver for economic development. Due to the drop in industrial activity, the demand for power fell from approximately 2,200 megawatts in 2004 to a current demand of 1,700 megawatts. An average of about 1,400 megawatts is being generated, hence leaving a deficit of approximately 300 megawatts. To meet the demand, Zimbabwe has had to import electricity from Kariba South in Mozambique and Eskom in South Africa, hence further straining the already stretched foreign currency reserves.
The construction of the hydroelectric project required two massive intakes to harness water from the vast Zambezi River. A massive piping system over 3 kilometers in length to effectively deliver a very high pressure torrent of water from the reservoir to the final stage of the project was also required, as well as the powerhouse, a hydroelectric generator plant housed in a cavern blasted from solid rock almost half a kilometer inside a mountain. This is how it works. Water from Lake Kariba is harnessed through the intake structure and flows through the headrace into the penstocks. As the water flows, the potential energy from the lake is converted into kinetic energy. The water is directed towards the turbine by stationary stay vanes in the spiral casing. The amount of water which drives the turbine is regulated by the guide vanes, which are a part of the governor system. As the water drives the turbine, the kinetic energy of the water is converted into mechanical energy. The turbine is coupled to the generator via a shaft, and as it rotates, the rotor, the rotating part of the generator, cuts the magnetic field of the stator, the stationary part of the generator. As the rotor cuts the magnetic field, alternating current is generated and stepped up to 330 kilovolts for transmission. Once the turbines are turning, the water is flushed out of the powerhouse and back into the Zambezi River, where it will continue downstream to serve other users of this legendary river, like Kariba South. The construction started with the blasting of 110,000 cubic meters of solid rock to form the massive turbine hall and surge chamber. Over 400,000 cubic meters of rock was blasted away for open areas such as the intakes, transformer platform, access tunnels, and the tail race area. Other major works included excavation and support of 6 access tunnels into the new plant, also known as adits. Each adit was blasted and excavated to serve various functions that included access to different parts of the underground construction area, such as access to intakes 7 and 8, upper and lower sections of the headrace tunnels, the underground powerhouse and its loading bays, access to the tail race tunnels and surge chamber. Before the engineers could start extending the existing power plant, they had to temporarily cordon off a section of the lake where the 2 massive intakes would be built. This area is known as the coffer dam. Slope trimming was carried out in parallel with soil excavation to clear the area for construction works to commence. The intake area consists of 2 concrete intake towers, which are 31.25 meters high.
In order to ensure the safety of the existing and extension powerhouses during the construction of the power intake, an 8-meter-long rock plug was placed in the downstream section of the intakes. It was then excavated when the intake emergency gate had been installed and was ready for retaining water. An access road to the intakes had to be paved with concrete to allow for water drainage along the road. At the start of the project, there was need to identify the source of aggregates and soil, concrete, stone and sand, and the correct mineral components required for this project. These were found at Charara Quarry, Gache Sand Quarry and Hurungwe, all of which were more than 40 kilometers away from the site.
For the 300 megawatts output, it's about 800,000 cubic meters of concrete, and that 800,000 cubic meters of concrete requires approximately 120,000 cubic meters of concrete stone, which is what we are quarrying out of this place, this Charara Quarry area, which is in the National Parks area.
Testing of the materials was done by the University of Zimbabwe's Institute of Mining Research, equipped with ZPC assistance. High above the powerhouse, the headrace tunnels were constructed. These were 100-meter-long pipes where water enters directly from the intakes. The headrace tunnels are linked to the penstock, which delivers water to the powerhouse at 144,000 litres per second. To prevent the high-pressure water from bursting out, the shafts were lined with reinforced concrete and steel moved in on specially set rails. It took precise and careful maneuvering to guide a pipe that big into place.
From the intakes, this whole area is concrete lined, then changes to a section of steel lining. So the main reason for changing from concrete lining is because as we approach our turbine, the pressure goes to almost its maximum in the waterways.
The design of the tunnels takes into consideration losses of energy and pressure as a result of resistance between the pipes and the water. This is called head loss. Next, workers carefully weld the sections together. A system failure anywhere in these pipes would flood the powerhouse in seconds. It is the most unforgiving of adversaries. The water from the headrace tunnel and penstock is discharged to the powerhouse, where electricity is generated. It took 2 years to carve out this massive underground cavern measuring 94 meters long, 24 meters wide, and 53 meters deep.
The main works were excavation and rock support. The concrete structures mainly included the encased concrete for spiral cases of Unit 7 and 8, turbine pit concrete, concrete for turbine layer, and concrete for sidewall and floor slabs of the bus bar layer. The turbo generators of Unit 7 and 8 are identical in their construction and consist of 8 main parts. The water inlet allows high-pressure water to flow into the turbine through the spiral casing. This surrounds the turbine and channels the water into the guide vanes. The draft tube is the first piece of the embedded part of a turbine. The runner is the critical part for converting kinetic energy into mechanical energy. As the runner spins, the generator shaft turns the rotor inside the stator to convert the mechanical energy into electrical energy. After the water is evacuated from the runner, it enters the draft tube, which comprises of a diffuser and an elbow. The diffuser redirects the water away from the turbines, while the elbow channels it towards the surge chamber. The surge chamber is situated downstream of the powerhouse and links the draft tube upstream and to the tail race tunnel downstream. The surge chamber is a large pressurized underground chamber that helps to regulate high-pressure water rises. Surge chambers are generally built high enough so that the water cannot overflow even with a full load on the turbine. The final stop for water used for power generation is the tail race tunnel. This water has already been used to rotate turbine blades and has served its purpose. Eventually, it joins the natural flow of the Zambezi River. The main construction works done at the tail race tunnel included excavation and support, tail race tower construction, and cofferdam construction and removal. The new plant generates a total of 15.75 kilovolts. This alternating current is then transmitted to the transformer platform. Here, a series of transformers step up the generated electricity to 330 kilovolts. The transformer platform is where the step-up transformers, accessories, ventilation and cooling equipment for the powerhouse are installed. From the transformer platform, the electricity is sent to the switchyard through a series of highly specialized cables that are routed up a long gradient in concrete-lined ducts. The switchyard is a subsidiary station of the electricity transmission and distribution system. The shunt reactor is the final station before the transmission of electricity to the national grid. It is an absorber of reactive power, thus increasing the energy efficiency of the system. It is used for reactive power compensation in long, high-voltage transmission lines and cable systems to ensure that no power is lost in the process. For safety and security purposes, the switchyard and shunt reactors are fenced by a galvanized chain-link fence with pipe posts and rails.
Through the Zimbabwe Power Company, the Kariba South Unit 7 and 8 extension is a vital sector as the Zimbabwe Agenda for Sustainable Socio-Economic Transformation (ZIM Assets) measure of success. A project of this magnitude involves a lot more than feasibility studies, funding, and going to tender to find suitable technical partners. Job creation for the locals was a key component in the agreement with the local stakeholders, chiefs, district administrators, and local council. At the project's peak, the staff complement grew to over 1,500 people on site, of which 263 are Chinese and the rest were locals from Kariba and surrounding areas.
There was a deliberate policy to say all the unskilled labor will come from the local community, which means those who come from the Kariba district, and of course part of the Urungwe is covered.
One of the things that gives me satisfaction is to look at the whole assortment of young people we have on the project. Technicals, non-technical professionals, accountants, technicians, journeymen, and everyone, all young, to realize that at the end of 40 months, we will have trained and empowered a young generation of engineers and technicians who can potentially be moved from this project to the other projects that we want to undertake.
And the fact that we're able to do that has made the sector, the region, and the continent look at our capacities, our competencies, our dedication, setting our reputation in terms of us standing shoulder to shoulder with perhaps the most productive nations in the world has come to the fore.
Tine vana vedu mamisha umu vakapinda mabasa ku hydro ku ZPC ko vari kushanda zvakuri kuti vakwanisa kunge vachiritira mhuri dzavo pavangakwana vese asi vakapinda yodoroti mpaka mabasa akaita sei vanhu vakapinda mabasa vari kuwanawo kamari kari nani kekuti munhu anenge aine pfungwa dzekuda kuriritira mhuri yake nekurongawo zveupenyu hwake anokwanisa kuronga zvinhu zvake zvakamuita sei zvakafamba pamatauriro avari kuita ivo.
This project, when it rolled out, we saw an improvement in business. More money was coming in the district.
Senine gandi ndakatoongora zvakanaka zvakawanda zvandakaona mukati kuti shuwa vanhu vanosvika kushanda kusvika pasaizi yakadai ende takaona makanaka musina kana maproblem.
Taatova nedzimba dzemalata muno vana vedu vakatitoka kuno vakaenda kusenza iko kumakisi saka vana ivavo vakaenda kunoshanda iye zvino mukaona so vateva netaundi mumisha mavo.
ZPC takabatana nayo chaizvo asati ambotsaukana nayo kana ivo pachavo ndofunga ri kuvimba nezvo.
Prior to the start of the project, intensive consultations with local stakeholders had to take place through the office of the district administrator. Such major stakeholders included the local chiefs. These consultations would later prove to be an important point of cooperation in the execution of the project. Equally important to the project was the Joint Operations Committee, a representative of supporting stakeholders such as the police, the Office of the President and Cabinet, the National Parks, the Zimbabwe National Army, and the local government, among other key stakeholders.
But one of the things that I think is important to state is the extent to which the project was closely monitored. At policy level, equally at ZPC employer level. I think it was one of the reasons why we were able to deliver on time and within budget.
Apart from job creation for the locals, the Kariba South Hydro Extension Power Project allowed for infrastructure development such as the classroom block for the O-level students of Mahombe Kombe community, refurbishment of the Nyamunga Stadium, construction of staff housing in Vatonga and Baobab, and the new Ruya Bridge.
In accessing our different sources of materials, we built a bridge across the Ruya River. That is another key corporate social responsibility initiative that we took. So not only will it save us in accessing Charara Quarry, but when the project is long done, that structure will remain in service, number one, to national parks, number two, to linking the communities in Charara, Gache Gache and beyond with Kariba.
As the backbone of the extension project, the Kariba Dam has a rich and tumultuous history, which will forever be an important part of the surrounding communities and the nation as a whole. Even now, it is the basis upon which many rituals and customs are based.
Project Chitanga. Chinoita chikaranga chatinoita. Chikaranga chochechi kuti bvunze kumasvikiro edu kuti munozvitendera here izvi hazvina here maripacations anozovapo kana padi kana project yakatangwa hapana njodzi dzinoitika here. Saka choda chikaranga chatinoita ichocho, pane kana zvatendwa pane zvatinoona, pane zvatinenge taita, kana zvisina kutendwa pane zvatinoona futi kana tadi kana tazviita. Saka isusu patakaita chikaranga chedu zvakatendwa zvakanakisa nemasvikiro edu, zvichirevera kuti banana kusvikana nhasi hatina matambudziko atiri kunyanya kunzwa sezvakamboitika pakutanga paya padam construction. Ndo mamwe mafeedza atainge tinauri chiti manje paya kufiwa kwapaita hapasi kuzofiwa here sezvaitika papi zvakamboitika paya. Asi kubva this project yatanga yeextension iyi, aiwa kana paine zviri kuitika isu kwatirasa zvasvika pachikaranga chedu nechiye, aiwa zviri kufamba ende zviri vana vakachengetedzeka.
Construction on this scale requires expertise from across the globe, with consultants coming from Canada and South Africa, high-voltage electric cables from South Korea, and heavy electromechanical equipment being designed and manufactured in China.
Currently we are on schedule, and it's a very tight 42 months construction period that we have, and at the moment we run about 60%, and to reach that was challenging, but teamwork is actually what got us up to this point. That means teamwork between ZPC, the client and ourselves, and then also once we started the construction it was with Sino Hydro, who was the EPC contractor.
The project saw the participation of players with global experience in various sectors. Hatch, the technical advisors, are a global international consultancy firm with experience in hydropower projects across the globe. KPMG, who played a financial advisory role, legal advisors Norton Rose and Fulbright, and Norconsult, who were the ZPC project management advisors. The Ministry of Energy and Power Development presided over a multi-sector project steering committee, which met every third month to review project progress and deal with stakeholder concerns and expectations. Hubei Hongchen were responsible for the manufacture and pressure testing of turbine inlet valves for Unit 7 and Unit 8. At this stage of the project, success of these tests was vital to the project timelines.
The factory acceptance test, in short FAT, this function is for us to check thoroughly the functions of the plant according to the technical specifications.
We have just tested the inlet valve for turbine number 8. And the result is just perfect. This is exactly what we have been looking for, and we are happy. For our other projects, we wouldn't hesitate to work again with HBHC from the time we engaged HBHC, from the time of design to manufacture and all the witnessing that we have done, we have been very impressed, and we look at the equipment that we see behind us and in front of us over there. This is impressive work.
目前这个产品是亚洲地区最大的水冷机精准方面，我们跟津巴布韦的这个公司合作很好。我们从产品的设计开始，从设计到加工制造过程当中，我们经过了多次的合作，双方都很愉快。这也因为津巴布韦和中国是老朋友，很好的朋友。
进展很顺利。中国水电希望这跟 ZPC 在津巴布韦这个项目，我们会认真履约我们的这个合同的这个关系，祝愿这个津巴布韦卡兰这项目顺利完成。
The Nari Group Corporation, a Chinese company, was responsible for the manufacture of the governor and SCADA system. These systems ensure that the entire plant runs within preset limits and allows for the adjustment of various components to satisfy the power demand at any given time on the grid. One of the largest manufacturers of hydroelectrical equipment in the world is HEC, Harbin Electric Corporation. They were manufacturers of various mechanical parts that formed the beating heart of the power plant. The design, manufacture and transportation of the transformers and reactors was done by TBEA.
Back in Zimbabwe, the generator transformers arrive, weighing in at a colossal 10 tons each. Transporting them has been a long, slow and incredibly delicate process. Each transformer requires 2 high-powered trucks to support its weight. Safety for the equipment and the crew is high on the agenda, and so the Zimbabwe Republic Police and other security forces are a must for this task. A journey that would ordinarily take 5 hours has taken nearly 3 days for the convoy to arrive in Kariba from Harare. Then starts the delicate and slow process of offloading the equipment.
Now we're witnessing the positioning of the generator transformers. It has taken almost a month since the transformers left the Durban port. Right now we see the team is busy rigging the transformer into position. It has taken almost 5 hours to put it on this position, on this platform.
The enormous efforts of the construction team paid off, and they are now on course to meet their deadline. Before power generation can begin, the intakes must be inspected for leaks.
For each unit, which is unit 7 and 8, we have got 2 gates, the emergency gate and the service gate. Now at the moment, we started by installing the gates. Once they have been installed, we fill the intake area with water so that we can perform leak tests.
This painstaking process was observed by both the local engineers and contractors to ensure that the years of hard work were nothing short of satisfactory.
In this area, any water leaking through the emergency gate is actually being measured in terms of its quantity. So we've got limits in terms of what can be allowable to pass through that gate. If it exceeds that amount, then that means there is some remedial action that needs to be done.
After double and triple checking the levels, the engineers were satisfied, chalking up another milestone towards the success of the project. Upon verification of functionality of the drainage and dewatering pumps, emergency and service gates, the removal of the cofferdam began at the lakeside. The successful removal of the cofferdam occurred in 2 stages. Stage 1 consisted of the removal of the first stage cofferdam by the regular method of blasting and mucking out when the water level was lower. Stage 2 comprised fully removing the rock ridge that was occupied by the second stage cofferdam by way of underwater excavation and mucking out. Another cofferdam at the tailrace side had to be removed after verification of functionality of the tailrace outlet gates and the surge chamber gates before exposing them to the water. The installed equipment was commissioned in stages. The generator transformers, switchgear, turbine speed load governor, turbine inlet valve, and other unit auxiliaries were commissioned and functional tests were done to ensure functionality of the units.
Our testing which we are doing today, we will carry out installation resistance test where we need to determine the installation integrity of the various conductors which are being used there, because if our installation is compromised, we tend to have some first earth faults or various faults which will be not very ideal in terms of light systems.
Once the switchyard had been installed to the satisfaction of the National Control Center, the switchyard was activated. Upon energizing the switchyard, the final commissioning tests were conducted once the National Control Center confirmed there was a load for the new installations.
We have got some engineers carrying out operations on local. We also have an engineer who is carrying out operations from a remote computer in the control room, and we also have operations like this operation that you're seeing now is being carried out from our National Control Center in Harare through what we call a supervisory control and data acquisition technology. We are doing that for all the equipment that you see in the switchyard.
For the engineers, this is the last chance they have to make sure everything works. One remaining job is crucial before they switch on the generators, a 7-day test run. The units will have to produce maximum power capacity of 150 megawatts for continuous 7 days. If this fails, the test run restarts.
Successful completion of those activities got us to where we are now, where we are saying the unit is ready to go commercial.
Christmas Day 2017, I was there in the powerhouse. We generated for the first time. It was synchronized to the grid. I remember the joy which was there on that day, people jumping, engineers, technicians, to say we have delivered.
Each unit has a runaway speed of 300 revs per minute, driven by the enormous water pressure made possible by the mighty Zambezi River. In the control room, the monitors show the incredible power being generated. Right now, both units are generating 300 megawatts. The project is completed. However, for the next 2 years, Sino-Hydro has a contractual obligation to rectify inherent defects during what is known as the defects liability period, after which they will fully hand over the 2 units to ZPC.
We are gaining quite a great deal of experience, both at a personal level and at a corporate level, because the capacity to deliver a project of this magnitude was not within ZPC until this project happened. So it will obviously make life easier when we go to more complex projects like Batoka, when we go to more complex projects like the Hwange Thermal Power Plant. It makes life easier because we will have developed, hopefully, a culture of proactive project delivery.
My company, we have business in 28, in 30 countries of Africa. We found out the Zimbabwean employees, they are well educated. That's one of the best. So that's make it easier for us to communication, and it's easy for them to accept the new technology.
The Kariba South Extension project is a very important project for Zimbabwe. Hence, the project was monitored continuously by the government and other key stakeholders.
In this monitoring, it involves a lot of activities. We also had to go and witness so many tests, even in China, at site, to make sure that things are going on well.
After 4 years of round-the-clock work, the project is completed ahead of schedule, in record time and within budget. Despite all the challenges, the power plant was running successfully for more than a month before it was fully commissioned on the 28th of March 2018 by His Excellency President Emmerson Dambudzo Mnangagwa.
As we switch on this power plant, let us keep the bigger picture in mind. We are opening the doors to the development of our beautiful country so that Zimbabwe can claim its rightful economic place in the global family of nations.
This project has been a pride to the nation. Sometimes you can't give a monetary value to it. We executed it within budget and on time, and it has delivered the technical parameters or the quality which was required.
At the moment, we have actually reduced the amount of power that we are importing because of Kariba.
When you come out of college, you are confronting the rest of your life ahead of you. You always wish and wonder whether you will have an opportunity to work on projects of a scale like this. But for it to be in Zimbabwe and for it to be arguably the biggest project ever undertaken in modern day Zimbabwe, it's an exciting thing.
This is an extraordinary engineering achievement. They have battled through the toughest conditions under immense pressure from the tightest of deadlines. Against all odds, the new units 7 and 8 have created a source of power that will last for decades.